Okay, so I hope that we're all invigorated after the break. So let's continue with this topic. So we've seen how we define the distance, the Wasserstein distance between two distributions. Okay. Now, I would like to show to you that the distribution robust optimization problem at the top of this slide can be reformulated as a simple convex optimization problem. So let me give you a high-level explanation of how this is going to work. Okay? So I'm going to use duality theory a lot. So I hope that most of you have seen how one can dualize a linear program to get the dual linear program. This is what I'm going to use. Okay? So the first observation is the following. We will first look at the inner maximization problem in this minimax problem. So the inner problem, that's nature's problem, where nature tries to hurt us as much as possible. Now, I've already mentioned before the break that the objective function of this problem is an expectation with respect to the distribution Q, and therefore is linear. So the objective is linear. And the feasible set is a convex set. So that means that the inner problem that nature needs to solve is a convex optimization problem. This convex optimization problem has a particular structure. Basically, it optimizes over distributions. So if my distribution lives on an infinite set, like the whole space or the non-negative orthant or a simple box, then basically my decision variables are the probabilities that are assigned to each point, and as there are infinitely many points, that means that this is an infinite dimensional problem, right? So the number of decision variables is essentially infinite. The number of constraints, however, is finite, because I essentially have just one constraint, that the Wasserstein distance between p hat n, the empirical distribution, and my q, which is my decision variable, should be smaller or equal to epsilon. Okay? So when we're formulating it, we'll have a few more constraints, but it's a finite number of constraints. Infinitely many decision variables, finitely many constraints. Okay? So this is a convex optimization problem. I will formulate it as a linear program, and we can actually then dualize it. The dual problem will no longer be a maximization problem, it will be a minimization problem. That's nice, because then I can combine the dual minimization problem from inside with the outer minimization problem to just get one single minimization problem. That's an advantage, right? Because we don't have solvers, at least not commercial standard ones, for min-max problems, but we have solvers for simple minimization problems. So by dualizing the inner maximization problem, we already transform the whole problem to a single minimization problem. Okay? Now the trouble is that the inner maximization problem, the original one, had infinitely many decision variables, but finitely many constraints. So its dual will have finitely many decision variables, which is nice, but infinitely many constraints. Okay? So if you have seen duality in linear programming, you know that the number of decision variables in the primal corresponds to the number of constraints in the dual, and vice versa. So by dualizing the inner maximization problem, we will end up with a single minimization problem with finitely many variables, great, but with infinitely many constraints. Problems of this kind are called robust optimization problems. Or I will show to you that this is equivalent to a robust optimization problem. And basically, what we're going to do then is we will use duality theory once again in the constraints to transform these infinitely many constraints to finitely many constraints. Okay? I don't think I should say more about this at the moment, but this high level, this is the plan. So I'm going to use linear programming duality as a main tool to derive these things. Okay? So that means at the beginning, I first would like to look at the inner maximization problem. And just to keep things simple, because we disregard the outer minimization for the moment, I'm just going to fix the x. Actually, I can completely drop it, right? Because we don't want to carry along clutter. So let's just look at the loss function that depends only on the uncertainty. And I solve a problem which maximizes, let me write max, over all distributions Q in the Wasserstein ball. So all distributions in a Wasserstein ball of radius epsilon around the empirical distribution P hat n. I maximize the expected value with respect to Q of a loss function that depends on psi. I drop the x because the x is fixed. You can think of it as it being there, but let's just ignore it. We'll introduce it later again. So that's the problem I would like to solve. I would like to study first. Of course, I can rewrite this problem as a maximization problem over all distributions Q. And now what I'm going to do is I'm going to assume that my Q lives on this finite set with k different discretization points, just to keep things simple, right? So this Q is actually a vector of dimension capital K, which contains the probabilities of the k different scenarios. And all of these probabilities are, of course, larger or equal to 0. Now, objective function is, of course, just copy it. It's the expected value under Q of my loss function. And now I have a constraint which says that the Wasserstein distance between Q and the empirical distribution should be smaller or equal to epsilon. So the distance, Wasserstein distance between Q and the empirical distribution P hat n is smaller or equal to epsilon. Okay? That's my optimization problem. So far I didn't do anything, right? So now let's reformulate this problem. And now I'm going to use the definition of the Wasserstein metric to reformulate this constraint. Okay? So the definition of the Wasserstein metric is this one here. I'm going to use this definition here. There's a question there. Did I make a mistake?
I'm not sure. I'm just wondering. Because now what we basically did is that we went from this Wasserstein ball formulation and introduced explicitly the distance metrics, right?
Basically, yeah. What we did from here to here is we used the definition of our Wasserstein ambiguity set.
Yeah, exactly.
Right? Which contains all distributions Q that have a distance of less or equal to epsilon from the empirical distribution. Yeah. It's just using the definition. I didn't do anything.
Yeah, that's fine. And then we said that our decision variable distribution needs to be non-negative.
Because these are probabilities.
Mm-hmm. Then would we also need a constraint that says that
the sum is 1.
Yeah. Or the integral.
In principle, we will see that this is implied by the. This is implied, right? So the P hat n is a distribution. So the sum of the probabilities of the empirical distribution is 1 by construction. Okay. So the P hat n, that corresponds to the P here. So we know that if we sum this equation here over L, then on the left-hand side, we get the sum over all k and L of pi kl. That's the total probability of the distribution pi. And here we get the sum of the PLs over all L. By construction, this is 1, right? Because this distribution is a proper distribution. So this sum is 1. Now for the Q, we don't know, because the Q is the thing we try to find. If we take the sum over k of the second constraint here, then we get on the right-hand side the total probability under the distribution Q. But on the left-hand side, we get the sum over all k and L of pi kl, which is the same as the sum that we got here, which we know is 1. So the solution of this problem implies that the sum of the Q case is 1. So we don't need to impose it. But that's a very good observation. Okay? Any other questions? Okay? So I'm going to use the definition. Again, I maximize over all distributions Q, so vectors with non-negative components. And now I'm just going to use the fact that this is a discrete distribution that lives on that set to re-express the expected loss as a sum. Right? So the sum will run over all scenarios from k equals 1 to capital K. Can you see that? Okay. It's just better for me. It's a bit, if I need to write down there, it's a bit inconvenient. So. The loss evaluated at scenario psi k multiplied by the probability qk of the scenario psi k. For discrete distributions, that's the definition of the expected value, right? So it's just a sum, and it's linear in our decision variables, the qk's. Okay, so that's easy. Now, this constraint here, I just reformulate by replacing the Wasserstein distance with this optimization problem, which is the definition of the Wasserstein distance. So I have a minimization here over all distributions pi with non-negative probabilities. The objective is to minimize the sum over all kl from 1 to capital K of psi k minus psi l times pi kl, subject to the two constraints, sum from k equals 1 to capital K pi kl equals to now p hat n L. So that's the probability that the empirical distribution assigns to our scenario psi L. And the sum from L equals 1 to K pi KL equals to Q K. This one is for each L. This one is for each K. This is the Wasserstein distance between Q and P hat N. And that should be, that thing should be smaller or equal to epsilon. The optimal value of this linear program needs to be smaller or equal to epsilon. Yeah?
I just have another question, again for the reformulation from the Wasserstein ball, because when we first defined this Wasserstein ball, we said that it is the intersection between the support set and the Wasserstein metric.
Yeah.
So we have the Wasserstein.
I look at all distributions on the support set, but I mean the support set is now this discrete set. And I only look at distributions on this set. So this condition that the distribution lives on this set is implicit here, because by design, I look only at distributions that assign probabilities to these case scenarios. It's by design.
Okay, all right, yeah, got it.
Okay? Mm-hmm. So this is a cumbersome object now. I have a maximization problem where the constraint involves a minimization problem. Okay? So we need to get rid of this minimization here because we don't like minimization problems in the constraints. This makes things complicated. But before we do that, actually, the empirical distribution is given to us, right? It's the uniform distribution on our training samples. And before I go on to reformulate this minimization problem in the constraint, or to remove it somehow, I would like to use the information about the empirical distribution. So I'm going to write the whole thing as, okay, now just copy everything, maximize over all q larger or equal to 0, sum from k equals 1 to capital K, loss evaluated at psi k times probability of scenario k under q, subject to, and now the minimum over all pi larger or equal to 0 of the sum from k and L from 1 to capital K, distance between psi k and psi L times pi KL, subject to, okay, the empirical distribution. Okay, so my support set is the set of these discretization points where you should think of this k as a huge number. Infinity, essentially, right? The empirical distribution is obtained by sampling n different points from the unknown true distribution. The unknown true distribution, of course, also lives on that set, right? We assume that this is the case. So the samples that you get are n samples from these capital K discretization points. Now the capital K, you should think of it as something that is much, much bigger than the n, right? N is the number of samples we have, which is naturally limited. capital K is just something we use to approximate, and we want the approximation to become exact, so we want K to be huge. Now the empirical distribution, so some of these discretization points will be equal to training samples, but most of them will be not. All of those discretization points that do not correspond to a training sample will have probability 0 under the empirical distribution, and all those that are sampled will have a probability of 1 over n under the empirical distribution. So the empirical distribution really lives only on n samples, not on capital K. So what we can do let me rewrite this, sorry. The Q distribution lives on potentially on all of the points from 1 to capital K. But the empirical distribution actually lives only on the n samples, so I can count from L equals 1 to capital N. Okay? And I only need to look at the joint distribution of Q and P, where the pi KL is such that the L corresponds to a training sample. Okay? So what my objective function looks like is really psi K minus psi L. Sorry. Psi K, that's the points to which the Q assigns probabilities. Okay? My P hat, my empirical distribution, assigns probabilities only to the training samples. And the training samples are psi hat I, right? So my sum goes over all the Ks, all the discretization points for the distribution Q, and psi is the random variable that follows the distribution Q. My psi hat, however, follows the empirical distribution, and this one lives on the training samples, psi hat I, where I goes from 1 to n only, right? And my mass transportation plan, this pi, can be denoted by pi ki. So that's how much mass of the distribution Q assigned from discretization point K to the ith training sample, right? This constraint here also simplifies. Here, I take the sum from K equals 1 to capital K of pi Ki. So I look at all the points, discretization points K. I count how much mass I move from any K to the ith training sample. And that must be equal to the probability of the ith training sample under the empirical distribution. Now, by construction of the empirical distribution, each training sample has the same probability, 1 over n. So this thing should be equal to 1 over n. Okay? So that simplifies. The other thing, however, the constraint where I sum over all training samples from I equals 1 to n, and look at all the probabilities pi ki, that sum should be equal to still to qk. That's for every k, and that's for every I. Okay? So using the structure of my empirical distribution, I could simplify, let's say reformulate, it doesn't look simpler, reformulate my Wasserstein distance. Okay, so that minimization problem gives me the Wasserstein distance between Q and the empirical distribution, and of course it still should be smaller or equal to epsilon. Okay? Does that make sense still? Okay. So that's a funny constraint. The solution of a minimization problem needs to be small or equal to something. Okay? Now it turns out we can actually drop the minimization here. If I have a minimization problem, any minimization problem, doesn't matter what it is, if we say the minimal value of this problem is smaller or equal to some number epsilon, then this is always equivalent to saying that my optimization problem has a feasible solution whose objective value is smaller or equal to epsilon. Okay? This is always the case. Let me give you an example. Let's look at all the buildings in New York. They're pretty tall. I can make two statements about the buildings in New York. I can say the smallest building in New York has a height of less than 100 meters. That is the same as saying in New York there exists a building whose height is less than 100 meters. Of course, if there exists a building that has a height of less than 100 meters, then the smallest building also has a lower height. On the other hand, if the smallest building has a height of less than 100 meters, then there exists one that has a height of less than 100 meters, right? The smallest is already such a building. So the two statements are equivalent. Okay? What I'm saying here, this is like, the buildings in New York correspond to the transportation plans. I'm saying the transportation cost of the best transportation plan is smaller or equal to epsilon. That's the same as saying there exists a transportation plan, pi, whose transportation cost, which is the objective here, is smaller or equal to epsilon, and that is feasible in this problem. Okay? So this is the same. I can write this now. Maximize over all q larger or equal to 0, sum from k equals 1 to capital K, loss of psi k, probability of scenario k, subject to, and now instead of minimize, I say there exists a transportation plan pi larger or equal to 0, which has the properties that the objective value is smaller or equal to epsilon. So that's the first property. Sum from k equals 1 to n, capital K, sum from I equals 1 to capital N, distance between psi I and psi hat. Sorry, psi k and psi hat I. That thing times pi ki, that thing is smaller or equal to epsilon. And the constraints. So the sum from k equals 1 to capital K, pi ki is equal to 1 over n, and the sum from I equals 1 to n, pi ki is equal to qk. Okay? So that's for every I, and that's for every k. Okay? That problem is the same. I've removed the minimum, but I have now a condition that says there exists something. Okay? Now, I can do two things to simplify this problem, and now I really mean simplify. The first thing is, in the objective function of my problem, I have the distribution Q. However, and that's my decision variable of the problem, right? Actually, let me do the other thing first. So, in this maximization problem, we optimize over Q, and we say there exists a pi that satisfies some constraints that depend on the Q. Actually, I can remove this constraint that says there exists a pi if I just include pi to the decision variables of the problem. So I can remove this thing, and instead of maximizing only over Q, I can maximize over Q and pi. Right? Of course, if I optimize over Q and pi, then my solver tries to find a pi that satisfies these conditions, which is the same as saying for a given Q there exists a pi that satisfies these constraints. Okay? So we shouldn't be misled by this quantifier there exists. It just means that we can add this object pi to our decision variables and nothing changes. Okay, So that's a huge benefit, because now we really have a single maximization problem. The minimum here is completely eliminated. We have decision variables q and pi, and these are my constraints. Now, I can even further simplify this question. I removed this minimum here.
Yeah, but that minimum constraint q, which is appearing in the objective function.
So for any fixed q,
It's not fixed, right?
yeah, but I maximize here over q and pi. I could do this sequentially. So maximizing sequentially over pi and q is the same as maximizing jointly. That is generally true. If you have two sets of variables, q and pi, right, you can either maximize jointly, or you can first maximize over q for fixed pi and then maximize pi, or the other way around. This will always be the same thing. So the order of maximization can always be interchanged. What cannot be interchanged necessarily is the order of maximization and minimization. Okay? So for those of you who study duality theory, interchanging max and min, there you need to make some arguments. You need to explain why you can do that. But interchanging two maxes or two mins, you can always do that. I could try to prove that. Other question?
Yeah. So basically, like from this board to the last one,
Yeah.
in this one we have a ball. In the middle one, we have a ball, and basically we want to first choose the distribution probability, the distribution function that is closer to the implicit one, the one that we gave, and then we maximize, let's say, the output of that expected value, right?
Exactly. So here we try to say our distribution Q needs to be close to the empirical distribution. Namely, it needs to have a distance of less or equal to epsilon. And the maximization here tries to find the worst case expected loss. So here we compute the expectation under Q, and we try to make this as high as possible so as to hurt the decision maker as much as possible. So nature tries to hurt us by forcing Q to be near to P hat. We don't give nature too much flexibility to hurt us, because this would lead to a very pessimistic problem. Okay? So that's what the constraint does. The constraint forces nature to pick distributions in a close neighborhood of radius epsilon around the empirical distribution. But within that freedom, nature tries to hurt us as much as possible. Yeah? Okay? Any further questions? So this looks already fine, right? We started from a very abstract problem, and we ended up with something that is actually a linear program. You see, the objective is linear in the decisions Q. This constraint here is linear in the decisions pi. This one is linear in the decisions pi. And this one is linear in pi and Q. That's a simple linear program. It's just a linear program. Of course, this constraint holds for all k, and we would like to think of k as being infinite. So this is a linear program with infinitely many constraints, as well as infinitely many variables, because we need a qk for each k. So this is a finite approximation of an infinite linear program. Before we continue, we realize that we can actually eliminate the variable q completely, because the q, thanks to this constraint here, can completely be expressed in terms of the pi. The q only appears in the objective function, the qk. I can drop this constraint and replace the qk by this expression in the objective function, and then I have an optimization problem over pi only. Let me write that down. So that's the same as maximizing only over pi larger or equal to 0. And then the sum from k equals 1 to capital K. And now the qk involves a sum from I equals 1 to capital N, distance between psi k and empirical sample psi hat I times pi ki. Right? I substitute this expression for qk in the objective function. Now I can drop that constraint. So the other constraints, they stay. So the first constraint was that the sum from k equals 1 to capital K, sum from I equals 1 to capital N of pi ki is equal to 1 over n. Sorry, that was that constraint. I forgot the first one, so let me add it here. And that holds for every I. And the first constraint is this one here, which I just need to copy. Sum from k equals 1 to capital K, sum from I equals 1 to capital N. Distance.
There's one extra sum.
Oh, what did I do? I messed it up, sorry. Let me start again. Yeah. Where's the sponge? It's too early in the morning. Yeah. Back to square one. Okay. Erase everything from your memory. We maximize over pi larger or equal to 0. Okay, this guy. Sum from k equals 1 to capital K. Sum from I equals 1 to capital N.
No sum again, no sum.
Sum again, because this q I want to replace by this sum. So this sum needs to go there, right? I can put it in front. Now the loss of psi k multiplied by pi I k. Pi ki. Okay, that's correct. Now, okay. Subject to sum from k equals 1 to capital K, sum from I equals 1 to capital N. Distance between psi k and psi hat I times pi ki is smaller or equal to epsilon. And the sum from k equals 1 to capital K, pi ki is equal to 1 over n for every I. Okay. So that simplified things a bit. We just have the decision variable pi, which is our transportation plan between the empirical distribution and our distribution Q, which is the one that nature chooses to hurt us. So this is still a maximization problem, like the one we started from. And I told you at the beginning of the lecture that I would like to dualize this problem to get the minimization problem, so that overall we end up with a minimization problem. Now, of course, that's now easy because so this guy, which is equivalent to nature's problem, is just a linear program. If I want to transform it to an equivalent linear program, I just take its dual. Okay? Now, I promised you that this dual would have infinitely many decision variables. Actually, the decision variables are pi ki. If k goes to infinity, this will be infinitely many. But the number of constraints are finite. This is the Wasserstein constraint with the radius epsilon. And here we have one constraint for each training sample. And there are n training samples, and the n is fixed. So this problem has a finite number of constraints, capital N plus 1, but a huge number of decision variables, capital K times capital N, where capital K will go to infinity. So we're dualizing this thing. Everyone knows how to dualize linear programs? Okay, I hope that most of you have seen that. I don't have the time to explain the duality theory here. So, but the trick is, you assign to each constraint a dual variable. So this is one constraint, the Wasserstein constraint. I assign it a dual variable lambda. This constraint here, there is a separate constraint for each sample. So I assign it a dual variable Si, yeah, which depends on I, the samples. So this is my primal problem. The dual problem will be a minimization problem because the primal is a maximization problem. So this is a minimization problem. And we will go over the variables, the dual variables that are assigned to the constraints. Okay? So we will minimize over lambda. And the lambda, the decision variable lambda, must be larger or equal to 0 because this is the dual variable to a less than or equal inequality constraint in a maximization problem. Okay? If you forgot these things, just trust me on that. Okay. I also need to minimize over the variables Si. The Si have no sign restriction because these are the dual variables corresponding to an equality constraint. The objective function is obtained by taking the right-hand sides of all the constraints, which are constants. Here is epsilon, it's a constant, and 1 over n, it's a constant. And we multiply these constants with the corresponding dual variables. So the objective function will be lambda times epsilon, this times this, plus Si times 1 over n. But now we need to take the sum over all I. So that I can write plus this 1 over n multiplied by the sum of the Si, where I goes from 1 to capital N. Okay? What are the constraints? Each variable in the primal problem corresponds to a constraint in the dual problem. So each variable pi ki for a fixed k and a fixed I corresponds to a constraint in the dual. So I need to check what is the coefficient of pi ki in each constraint. Like in this constraint, the coefficient of pi ki is this distance between psi k and psi hat I. And in this constraint, the coefficient of pi ki is just 1. So basically, the coefficient of this one multiplied by the dual variable Si, that's just Si. Then the coefficient of pi ki in this constraint multiplied by lambda, that's just plus lambda times distance between psi k minus psi hat I. Right? That's how I construct the constraint in the dual problem. So I take the coefficients of the same primal variables, multiply those coefficients with the dual variables of the constraints, and add them up. That's what I do here. Trust me on that. Okay? And the right-hand side coefficient of this constraint is equal to the objective function coefficient of our variable, which is L of psi k. Okay? And this needs to be a greater than or equal inequality, because this is the constraint that is dual to the variable pi ki, and the pi ki is non-negative. So this needs to be an inequality. Okay? And we have such a constraint for every variable pi ki. So this constraint holds for all I and for all k. And that's it, basically. So that's my dual problem. That's equivalent to the primal one. Okay? So this is, it looks much simpler than the beginning. It's still a linear program. As you can see, the objective is linear in lambda and the SIs. This constraint is linear in the SIs and the lambda as well, right? This guy is a constant. This guy is a constant. The number of decision variables in this problem is finite. We have 1 lambda, and we have capital N SIs. The capital N is fixed. The number of constraints will blow up, because when we let k go to infinity, we will have infinitely many constraints. Okay. Now, I want to reformulate this constraint a bit. I want to move everything that depends on psi k to one side, and I want to move the Si to the other side. Okay? So that's just rearranging things. I will delete this, but I hope you have already copied it. Okay. I can start again. Let's see. Maybe we can start here. So it's the minimization problem over lambda larger or equal to 0 and over Si, where I minimize lambda times epsilon plus 1 over n sum from I equals 1 to capital N Si, subject to, and now my constraint is that Si is larger or equal to L of psi k minus lambda times psi k minus psi hat I for every I and for every k. Okay, that's just rearranging things. Now the left-hand side depends on k, and I want this left-hand side to be smaller or equal to Si for every k. So I can actually drop the for every k and introduce a max here. I can take the maximum over k. Let's look at the buildings of New York again. I can make two statements about them. I can tell you that all the buildings of New York have a height of less than 600 meters. Don't know whether this is true. All the buildings of New York have a height of less than 600 meters. That's the same as saying the tallest building in New York has a height of less or equal than 600 meters. That's what I'm doing here, right? By putting a max here, I'm saying that the maximum value of the right-hand side should be smaller or equal to Si. If I drop the max and put the for all k, I say for every k, the right-hand side needs to be smaller or equal to Si. It's the same thing. Okay. Now actually, if I maximize over k here, then I basically maximize over all the discretization points that I've chosen. Now I can actually let this number of discretization points go to infinity. If I choose enough discretization points so that in the end I fill the whole set psi from which I started, which could be the whole space, or could be a box, or could be an ellipsoid or something, right? Then instead of maximizing over all k, I can just maximize here over all psi. So I can maximize over all psi in the capital set psi. Okay? And now my discretization is completely gone. Now I have exactly reformulated. So this problem here, one can rigorously prove that, but I think it's intuitive, is exactly equal to that problem, even if the distribution Q lives on a set psi that is infinite. Okay? Which could be a polyhedron. So this looks pretty easy, right? Actually, I can even more simplify that. You see, we minimize the SIs. The SIs have a coefficient that is positive. So at optimality, the SI will be as small as possible. The SI only appears in this constraint. So the optimal choice for SI is equal to that right-hand side. So this whole problem can be reformulated as an optimization problem over only one variable, lambda, that is larger or equal to 0, where the objective is to minimize lambda times epsilon plus the sum of 1 over n, the sum over all I from 1 to n of the maximum of psi in psi, the loss function of psi minus lambda times the norm of psi minus psi hat I. Right. So that's basically, that's an intermediate final result, right? Well, sounds a bit awkward. These two things are equal. So we started from nature's problem. We reformulated it as a minimization problem over a single scalar variable, lambda, with this objective function. Now this objective function is no longer linear because we have a max inside here, right? And that's still potentially complicated, but this already looks much simpler to me at least than from where we started. So you can see, if our loss function depends now on x, so we could introduce the x again, then there would be an x here, right? I could combine, now I could substitute this minimization problem for the maximization problem up there, and I can combine it with the minimization over x, and that means instead of minimizing over lambda, I minimize over lambda and x in capital X. So this is equivalent to my distribution robust optimization problem. Okay? This already looks simpler. Okay? Yes?
Something bad.
Let's see. So basically, I moved this lambda psi hat minus psi k minus psi hat norm to the other side. And then I had the SI on this side, and everything depended on psi k on this side. And the constraint should hold for every k. So then instead of having a for every k, I said that the maximum of the right-hand side over all k should be smaller equal to Si. Yeah? That's where I got basically here. And then instead of maximizing over k, I said when k goes to infinity, we can maximize over all psi in the uncertainty set. Okay? And then from here to here, I eliminated the variable Si, because I know that at optimality, the Si needs to be equal to this right-hand side. Okay? So we're not done, because this one we cannot solve yet, right? It's a min-max problem. It's actually, this is a robust problem, right? It's a robust optimization problem. You choose a decision lambda and x, and nature chooses then an uncertainty realization psi in the uncertainty set psi to hurt you as much as possible. I mean, the physical interpretation is not completely clear, but formally, this is exactly a robust optimization problem, right? Where your decision is lambda and x, and nature's decision is a realization of psi in the uncertainty set. So now I would like to show to you that this problem here can be reformulated as a linear program, a simple linear program under some conditions. And I need to write down what these conditions are. So the assumptions are the following. First, I assume that the uncertainty set psi here is a polyhedron. So the set psi is equal to the set of all variables psi that satisfy the condition c times psi is smaller or equal to d. So these are just linear constraints. C is a matrix and D is a vector of appropriate dimensions. This is a polyhedron. Okay? Actually, C and D could be 0, then this is the whole space. Okay? Doesn't matter. The other thing, I'm going to assume that my loss function is piecewise linear. So that's the first assumption. And the second assumption is that the loss function of x and psi can be written as a maximum over j in some finite index set capital J of a vector aj that depends on x transpose psi plus some scalar bj that depends on x. It's too low here. Okay. What does it mean, right? For any fixed j, this thing here is a linear or an affine function in psi, but the coefficients depend on x. And now I take the maximum of these affine functions for all j. So if I have different linear functions, I take the maximum of those, I get a piecewise linear convex function. Right? This function, L, for a fixed x, is piecewise linear and convex in psi. Okay. That's basically the assumption. Later on, I will assume that the coefficients aj, this is a vector, and the scalar bj, that they also depend linearly on x. But for the moment, we don't need that. Okay? Now, I told you at the beginning, I need linear programming duality. We've already used that once. We will use it again. The other thing I need is, we have this norm here, right? So we need to talk about norms a bit. Okay? So what is a norm? A norm is, well, basically a function that assigns a vector a length. Tells you how long a vector is. And it's positive homogeneous, it's subadditive, and the norm of a vector is 0 if and only if the vector is 0. Right? Now the thing I'm going to use is the so-called dual norm. Any norm on a finite dimensional vector space can be assigned a dual norm, and I'm going to need that one. So the dual norm I denote the dual norm of a vector v by the normal sign of a norm, but with a subscript of a star. Okay? And I define this as the solution of a maximization problem, where the objective is to maximize v transpose xi over all xi whose norm, and that's the original norm, is smaller or equal to 1. Okay? Who has already seen something like that? Okay, few people. Okay. It's not a difficult concept. In this maximization problem, we look at all the vectors xi that have a length of at most 1. If this norm is the normal Euclidean norm, right, then this is just a normal ball in the space. It's a normal Euclidean ball, right, as you would imagine it. We're maximizing now the inner product of v transpose xi over this ball. This gives me a number that is larger or equal to 0, right, because, I mean, I could choose xi equals to 0. That would satisfy the constraint and would have an objective value of 0. Since I'm maximizing, either xi equals 0 is the optimal solution, or I get something that has a higher objective value. So this gives me something that is positive. Okay? You can prove, and it's an easy exercise, that if the norm that you use here in the definition satisfies these three properties I mentioned, so it's positive homogeneous, it's subadditive, and it's, well, how do you call that? I think it's called positive definite. So it's 0 if and only if the vector xi is 0. Just using these three properties, you can prove that the dual norm, defined in this way, will also satisfy these three properties. Okay? Now, for practical purposes, you don't need to know much about this. If your norm, the original norm, is the 2 norm, so that's a Euclidean norm, then it's easy to prove that the dual norm is also the Euclidean norm. Okay? More generally, if your original norm is a p norm, where p is a number larger or equal to 1, then the dual norm is a q norm, where 1 over p plus 1 over q is equal to 1. You can verify that if p is 2, then 1 over p is 1/2. For this to be equal to 1, q needs to be 2 as well. So this needs to be 1/2. So that thing implies that thing, right? Norms you would typically want to use are the Euclidean norm, right? That's just the most common thing you would use. That's Euclidean distances. That's how we measure distances in real life. Other norms that are interesting are the 1 norm and the infinity norm, right? So if p is 1, then you get 1 here. This needs to be 0, so q needs to be infinity, and vice versa, right? And you know the definitions of the 1 norm and the infinity norm, right? The 1 norm of a vector is the sum of absolute values of all components, and the infinity norm of a vector is just the absolute value of the maximum of absolute values of all components. Okay? These two norms are nice because they are sort of polyhedral, right? They lead to linear programs in the end. So that's why we like them. Okay. So I would like to look at the worst case expectation again. And I would use the reformulation that we derived before as the minimum over all lambda larger or equal to 0. And I will introduce my SI variables again, right? I'll go back to this formulation, okay? I use this one, okay? So my objective is lambda epsilon plus 1 over n, sum from I equals 1 to n Si, subject to, and now I have this constraint here. And I substitute my definition for L of xi in it. So I have the maximum over all xi in xi, which I have from here, right? But the L itself is a maximum over j, maximum over j in j, and then I have a j of x transpose xi plus bj of x. That's my definition of the loss function. And then the rest is just minus lambda norm xi minus xi hat I. And that should be smaller or equal to si for every I. Okay? So the only thing I did, I used the definition of my loss function as a maximum of linear functions. Now I have a maximum over xi and a maximum over j, and we said before that the order of maximum doesn't matter, so I can move that thing out. But then I have that the maximum of something is smaller or equal to si for every I. And that's the same as saying that whatever is here is smaller or equal to si. Sorry, the maximum over j, okay, the maximum over j of this expression, which is a maximum of xi itself, okay, is smaller or equal to si for every I. I can drop this maximum over j and just write for every I and for every j. That's the argument with the buildings in New York. Okay? This is okay because the i's enumerate the samples, which are finitely many, and the j's enumerate the pieces of the loss function, which are also finitely many. Okay? Now there is another thing I can do. Okay. Actually, there's one thing about norms I wanted to mention. If I construct my dual norm, I can construct the dual of the dual norm, and it turns out that the dual of the dual norm is the original norm. Okay? So the dual of the dual norm is the original norm. And this means that if I have the norm of a vector xi minus xi hat I here, I can write this as the maximum of xi minus xi hat I transpose v, where I take the maximum over all v with a dual norm of less than or equal to 1. Okay, that's this thing.
Excuse me.
Yes?
Why did you change the objective function back to that form again? Because last time we stopped at the minimum and...
So it's nice to represent it in that way.
yeah.
But I needed to go back, I wanted to go back to this formulation here with the SIs, even though I could eliminate the SIs, but it turns out that this will simplify the derivations I'm going to do. Okay? It just simplifies. It's my choice. I can do it, right?
So that comes from which one?
So I used this formulation here over here. What I changed is, instead of L of xi, I used my definition of L of xi, which is this one here. So I substituted this thing into here. That's basically what we have here.
I have a question as well.
Yeah.
So what the set J, what is it in this definition?
This is a finite set. So yeah, think maybe maybe the objective function is, maybe the loss function has two linear pieces, then J is the set of 1, 2, right? Think of it as a finite set. Think of it as the integers from J equals 1 to some number. Yeah?
Like J arbitrarily defining.
Depends on what your objective, what it is, right? I mean, this is your loss function. If you solve a news vendor problem, then you depending on how you formulate, you may have 2 or 3 pieces. If you know the news vendor problem, yeah?
Okay.
Then this would be exactly of that form. Yeah. Okay. So I can write the norm as the dual of the dual norm by using this definition, right? Now, if I multiply this norm by lambda, I can actually include this lambda in the definition here. Instead of looking at all the v that are smaller or equal to 1, I can look at all the v that are smaller or equal to lambda. This will be the same thing. Okay? It's easy to verify. Okay? The other thing that we should pay attention to is that basically we want to express this dual norm as the solution of a maximization problem. Sorry, we want to express this norm as the solution of a maximization problem in every constraint, and the constraints, they are indexed by I and j. So my decision variable v here in this maximization problem needs to depend on both I and j. Okay? Shouldn't be the same for different i's and j's. Okay. So I need to think about how we do this. I don't think I will get through all of the derivations. Maybe I just do one or two more steps and then I tell you how it ends, okay? So that I can show you some more pictures. Okay. So let's look just at this one constraint for a fixed I and j, because the objective function is anyway easy, right? It's just a linear function of lambda and the si's. Let's look at one fixed I and j. My constraint is to maximize over all xi in xi aj of x transpose xi plus bj of x minus the maximum of all vij with a dual norm of less or equal to lambda of vij, this is vij as well, transpose xi minus xi hat I smaller or equal to si. Okay? This is a minus in front of a max. I would like to move this max outside here, but because I change it with a minus, it becomes a min. Right? That's something that you also learn in linear programming class usually. Minimizing C transpose X is the same as maximizing minus C transpose X, right? Well, if you multiply if you multiply the result at the end by minus 1 again. So that means interchanging a multiplication by minus 1 and the maximization. So minus max is the same as min minus. Okay? I can move that max out here, but I get a min. So that's what I'm doing, right? I remove it from here, and I put it here. Minimum over vij dual norm smaller or equal to lambda. Okay, that's a bit small. Sorry for that. Let me write it again. Okay.
Then it's plus, right?
It's minus. There was a minus here. It stays here. Yeah? Minus max. The max goes out. Minus max is equal to min of minus. Yeah? So the minus stays. Yeah. Okay. Now, it turns out that I can interchange here even the min and the max. I can move this min outside. The reason for that is that the function here is linear in xi for every fixed vij and is linear in vij for every fixed xi. So this is like a saddle function. If you solve a max-min problem, where the feasible sets are of both the maximization and the minimization are convex, and your objective is a saddle function, then typically you can interchange min and max. Okay? So we can interchange here. And then we have a constraint that says the minimum of something over all vij is smaller or equal to si. Now I can drop the minimum again. And it's again an argument with the buildings in New York. If I say there exists, if I say the smallest building, so the minimum, the smallest of all buildings in New York has a height of less than 100 meters or 50 meters, then it's the same as saying there exists a building in New York whose height is less than 50 meters. So this constraint is therefore equivalent to saying there exists a variable Vij, a vector, with the following properties. It needs to be feasible, so the dual norm of Vij needs to be smaller or equal to lambda. And the objective function needs to be smaller or equal to Si. The objective function is the max, which is inside, right? Max xi in xi, Aj of x transpose xi plus Bj of x minus Vij transpose xi minus xi hat I should be smaller or equal to Si. Okay. And now I'm going to do a shortcut, okay? I'm just telling you what needs to be done. And it's easy to finish it. But it will take some time, so I don't want to do it. The constraint here has been reformulated as this thing here, where we have, there exists a Vij that satisfies some conditions. As we've seen before, this Vij can just be added to the decision variables of this problem. And these things will become constraints of this problem. Okay? Like before, when we dropped the condition there exists a transportation plan pi. Can do the same thing here. There exists a Vij, can be added, so the Vij can be added to the decision variables. Then we have this constraint here, which is actually a convex constraint. It says the norm of some vector should be smaller or equal to lambda. If this is a 2 norm, this is actually a second order Kuhn constraint, so this would be easy. If this is the 1 norm or the infinity norm, this can be reformulated in terms of finitely many linear constraints. Okay? This thing here is still complicated because it says the maximum over all xi of something that is linear in xi is smaller or equal to Si. Here I can do something I've already done. This is actually a linear program because the feasible set is a polyhedron. That's the feasible set of a linear program. And the objective function is linear in xi. So this maximization problem I can dualize to get the minimization problem. And then it's again an argument with the buildings in New York where the smallest building is smaller or equal to something. It's the same as saying there exists a building that is smaller or equal to Si. And that means the dual variable I pick up here can also be added to the variables of the original problem. If I do this, in the end I'm done. Everything is just one linear program. So I guess what I told you at the beginning is true. You only need linear programming, but it's in a rather sophisticated way, maybe. Okay? But it's just linear program. Okay. Is it okay if we leave it at this? I think you get the idea, right? It's always you dualize stuff, and there exists constraint can be reformulated as a constraint with a minimum. A for all constraint can be reformulated as a constraint with a maximum, and then these kinds of ideas you just use them. Okay. Okay. So I have also something similar on the slides, not just for linear programs, but for the general case. So that's our worst case expectation problem. We've seen that we can reformulate the worst case expectation problem as a problem over the distribution Q and the transportation plan pi. If you don't write it out as in sums but with integrals, that's what it looks like. Here is a visualization of the optimal transportation plan that transports a discrete distribution on 4 points. This one here, right? To a Q which looks like a typical distribution. And somebody asks about what the optimal transportation plan looks like. In this case, it would look like that. So it's a very weird distribution which has like 4 different kinds of shark's fins that look out of the plane, right? So it's a very degenerate distribution. Okay, we dualize the problem, we get something like that. That problem is something like so this one, where is it? No, this one doesn't look like one we've seen. Okay, so this one looks like one we've seen, okay? That one we've derived, okay? Right, that one is, which one is it? That's this one, right? This one here, okay? And now, if you do the rest of the steps that I just mentioned to you, then in the end you will end up with a convex optimization problem. So if you don't insist on an uncertainty set that is a polyhedron, and if you don't insist that the loss function is piecewise affine, then this is what you get, right? And to understand this one, you need to know some convex analysis, which I assume not everyone is familiar with. What I can tell you is that this is really a finite convex optimization problem. What shows up there is the so-called convex conjugate of the loss function. This is this minus L with a star. What also shows up is the dual norm of some variable, which we have seen where it comes from, right? And what also shows up is the so-called support function of our uncertainty set. That's also an object that is studied in convex optimization, in convex analysis, okay? So you can reformulate your problem as this thing here. This is a finite convex program. Okay? That means we can solve it in polynomial time. And you can combine it with the minimization over x. And under appropriate conditions, the overall problem is tractable. The problem size here actually grows proportionally to the number of samples. You see that for each sample, you have a convex constraint. And so in some settings, depends really on the specifics of the loss function and the specifics of the support set. But there are some interesting cases where this problem is really in the same complexity class as the sample average approximation problem. It is more complicated, but from a computational point of view, not substantially more complicated. Okay? Okay, so that's the main thing. Now I think you can relax. I just want to show you some more things. So first of all, we looked at this example before, right? We solved the portfolio problem with the sample average approximation method. And we've seen that the in-sample results are too optimistic. That's the green histogram. And the out-of-sample results are too pessimistic. And that's the red histogram. Now let's see whether the approach here actually can improve this outcome if we give the optimizer only 30 samples, as we've done for the SAA method. If we solve this problem with the distribution robust approach, and we again compute the in-sample histogram and the out-of-sample histogram, we see several things. So the out-of-sample performance is much more narrow, much more peaked. So you have much less uncertainty about what you're actually going to get in reality when you implement the optimal solution of your problem. And somehow, luckily, this histogram of out-of-sample performance also moved closer towards the ideal optimal solution of the problem. To be honest, this is not something that was necessarily to be expected. I guess this is somehow it's just there's maybe not a completely convincing theoretical explanation for that. It just happens to work. Maybe the reason for it is that our certificate, so the J hat, this is the number for which we guarantee that it will be large or equal to the out-of-sample performance with high probability. In this case, this J hat is the optimal value of the distribution robust optimization problem. And of course, that's the thing we minimize. So if we try to push the certificate to the right, then it means that we push the whole red histogram somehow to the right. Okay, but I don't have a better theoretical explanation for that. This is quite systematic, so it's not just in this example. In many examples we've studied, you see an improvement along these lines. Of course, you cannot expect something perfect, but you can definitely improve on the sample average approximation. Okay. Now, don't look at the math, okay? Completely forget about that. So just listen to me. We derived a convex program that is equivalent to the worst case expectation. So we started from this guy here, and we found at the end I didn't fully show it to you, but we found a convex program that is equivalent to that, which is a minimization problem. Now, me personally, as a admirer of convex optimization, whenever I see a convex optimization problem, I feel the urge to dualize it. So I dualized this finite convex program, right? Because I started from an infinite dimensional problem, maximization problem. I ended up with a finite convex program. I dualize it. I can do that systematically. I get another finite convex program, but this is a maximization problem. Okay? And that's again equivalent to where I started from. And that's the problem on this slide. Now, this problem has a very interesting interpretation. This problem can be interpreted as a worst case expectation problem, where again you take the worst case over a set of distributions that have a Wasserstein distance of at most epsilon from the empirical distribution. But this time, you don't look at all distributions supported on Xi. You only look at discrete distributions on Xi that have as many discretization points as the empirical distribution, so capital N, and which assign to each discretization point the same probability 1 over n. Okay? So this is a very interesting structural insight. That means even if we allow the nature to optimize over all distributions in the Wasserstein ball, nature will get the same result by only taking the empirical samples and moving them around. Not too much, because so the variable qi here, that's the displacement of the ith empirical sample. So nature will only displace the ith sample by a vector qi, and the total sum, or the average of the total displacements, so the 1 over n sum of norm of qi, needs to be smaller or equal to the Wasserstein radius. Okay? That's how nature is limited in moving around the points. So that tells us that the worst case distribution is always a discrete one that looks like the empirical distribution, just that the samples are perturbed. This was not at all clear from the beginning. And we can actually get that worst case distribution by solving this problem here, which is also a tractable convex program. Okay? Let me show you an example. So here, the loss function is a quadratic function that is concave. It looks like that, right? And the maximum of the function is in the middle. So the ellipsoids here, they represent the level sets of this distribution, of this loss function. Now, the red dots here, these represent the samples of my empirical distribution. Now, of course, they're not randomly selected, right? I just put them on a grid neatly so that we can actually better see what's going to happen. Now, I want to calculate the worst case expectation of this quadratic loss function over all distributions in a Wasserstein ball around the empirical distribution on the red dots when I make the radius bigger and bigger. Now, simple case. When the radius is 0, my ball just consists of the center. And the center is the empirical distribution. So when the radius is 0, I just evaluate the expected cost under the empirical distribution. If the radius gets bigger, then we know now that nature will try to move around these red scenarios to hurt us. Now, the loss function is maximal in the center of the plane. So nature will try to move all these scenarios to the center, right? And I'm going to show you a video now that shows you how nature pushes these samples towards the center as it gets more freedom, so as we increase the Wasserstein radius. We will see that nature will first move the scenarios that are far out. The reason for that is that the quadratic loss function is steeper outside. And by moving those scenarios first, nature can hurt us most, right? In the extreme case, in the end, we will see if the radius becomes huge, then nature is not restricted at all anymore, can move the probability mass wherever it wants. And in the worst case, it will move all the probability mass to the center of the plane, which is the maximum of the loss function, which corresponds to robust optimization, where you find the worst case scenario, right? Okay, so that's what it looks like. Oops. Something went wrong. Sorry about that. Let me try again. Yeah, don't know what that was. So you see that the outer scenarios are moved first, and then they're collapsed together, and in the end, if the radius becomes very big, all the probability mass is concentrated in the center. As a transportation distance here, I didn't use the Euclidean metric. I used the one norm, and that's why this looks almost kind of edgy, right? But depending on what norm you use in the definition of the Wasserstein metric, so depending on this thing, right, this norm, you will get a different solution. But I mean, qualitatively, it will be the same. Okay. So just to give you a flavor of what you can do with this, so far we looked at the situation where the loss function, so this result was for a loss function that is concave, so it looks like that in the uncertainties index size. However, all the results, so all the tractable reformulations, can also be derived for loss functions that can be written as a pointwise maximum of different concave functions. And that is useful because taking a maximum of concave functions gives you really a lot of freedom. It's basically every function you can think of, you can approximate by a maximum of concave functions. Okay? And for all of those, so the only thing that matters is that these are finitely many concave functions. But by allowing many pieces, you have a lot of freedom. So here are some examples of exact reformulations. So if your uncertainty set is a polyhedron, like we defined here, right, this thing here, and if your loss function is either a maximum, a pointwise maximum, or a pointwise minimum of affine functions, right? So it either looks like, so my pointer is somehow out, my battery is low, but like the convex piecewise linear function or the concave piecewise linear function, in both cases you can get tractable reformulations. The exact reformulations are shown here. You will see that there are actually linear programs in all the variables that appear there. So everything that is blue is a decision variable. Everything that is green is a sample, right? The only constraint that is nonlinear is the one that involves the dual norm. Now, even that constraint could be linear if the norm that we used in the definition of the Wasserstein metric is the one norm on the infinity norm. In this case, in both cases, these exact reformulations are simple linear programs that you can easily solve, right? With Cplex, Gurobi, whatever. You're the solver of your choice. You can also solve two-stage stochastic programs in principle because in a two-stage stochastic program, the loss function whose expected value you compute is essentially the solution of the second stage problem. Now, if the second stage problem depends on the uncertainty only in the objective function, then your loss function is concave and piecewise affine. So then the results apply. If the second stage problem is affected by the uncertainty only in the constraints, then your loss function is convex and piecewise affine. So in both cases, you can derive these pieces, that can be done systematically, and you can use the formulas from the previous slide to get exact reformulations of the worst case expectations of those. Okay? To be honest, there is one catch. The number of pieces that you need for the case with constraint uncertainty is typically exponential in the dimension of the second stage problem. So there you may need approximations to, it will be a linear program, but it could be a huge one. Okay? It is a finite linear program, but it could be huge. And you may need additional approximations to actually solve this in practice. Another interesting case is that you can even look at chance constraint programs or uncertainty quantification problems. So what is an uncertainty quantification problem? That is a problem where you try to find the worst case probability that your random vector xi falls inside or outside some set. Okay? So say you could think of xi as the state of a system that is uncertain, and you could assume that your system operates safely if the state of the system is inside some set or outside some set, right? This could be the flows of your, the network flows of your transmission system, and the system is safe as long as these flows are within certain limits that respect the thermal capacity of your transmission lines. So if you only have seen historical data of the uncertainty, then you could ask, what's the worst case probability that my system is unsafe, where I take the worst case over all distributions in a Wasserstein ball around my empirical distribution. It turns out that what I derived can be used to quantify this worst case probability by solving a linear program. For example, imagine that we would like to calculate the worst case probability that my random vector xi is inside the polyhedron A. So I would like to maximize the probability that xi is in A. Now the probability that xi is in A can be written as the expectation of the characteristic function of the set A. That function is equal to 1 if xi is inside A, and it's equal to 0 outside. So I bring this problem back to a problem of finding a worst case expectation. The indicator function of the set A is visualized by the red function on top left. Now, why can we use our reformulations? Because this indicator function can be understood as the maximum of two concave functions. Okay? The first function is just a function that is constant 0, which is visualized in green on the top right. That's, of course, concave. And the other function is the function which is equal to 1 inside the set A and equals to minus infinity outside. And this is also a concave function, right? So that's why we can reformulate this problem actually as a linear program in the end, if you use the one norm or the infinity norm. So you can find worst case probabilities of such sets by solving just a linear program. We can also find the worst case probability of xi being outside of some polytope. Again, the probability that xi is outside of a polytope is the same as the expectation of 1 minus the indicator function of that set. And this can again be written as a maximum of finitely many concave functions. So that's sort of visualized at the bottom at the right. These finitely many functions are again the function that is constant to 0, which is the red function. And then for each facet of the set of the polyhedron A, there is one function which is equal to 1 if that particular constraint corresponding to that facet is violated, and that is equal to minus infinity otherwise. If you take the maximum of all these guys, as visualized there, then you recover basically the characteristic function of the complement of the set A. Again, you can use the standard, the techniques I've shown you, the general techniques applied to this setting to reformulate this as an LP. Okay, so here's another visualization. Let's say my polyhedron A is the blue diamond in the middle here, and my empirical distribution is again the uniform distribution, the red dots that are nicely arranged on a grid here. So on the left-hand side, I would like to show to you what happens, or what the worst case distribution looks like when the Wasserstein radius becomes big. So nature tries to move probability mass inside the polyhedron, because nature tries to hurt us, right? In this here, the interpretation is that if xi is inside the set, then it's bad for you. So the set A is like the unsafe set for our system. Okay, so let me show you the video. You see that the closest points are moved first towards the set. Those points that are already inside are not moved at all. And eventually, as the radius is huge, then all the points will move inside, and we get the trivial upper bound on the worst case probability of 1, right? That we would have known that up front without any calculation. On the right-hand side, I show you the opposite. Now, let's assume that the system is safe if we're inside the diamond and we're unsafe outside. If nature tries to hurt us, it will try to move the points outside of the diamond. Okay? And it will do that in a very funny way, as you will see. So I'll start the video now. So you see that the points are no longer moved. They're also split up and can combine again. And it looks quite psychedelic. But eventually, the end result is the same. So, it's what to be expected. Nature moves all the points outside of the diamond. And that means then the worst case probability of being outside is 1. Okay? The reason why nature splits or can split up points here is because in this case, we don't have a single or just two concave functions. The loss function needs to be represented as a maximum of 5 different concave functions. One for each of the 4 facets and one for the constant 0. And in this case, it turns out that the worst case distribution obtained with our method can have more discretization points than the empirical distribution. And the probabilities can change as well. But all of this was computed, all of these things were computed by solving simple linear programs. Okay. There's one more experiment I would like to show to you. So we studied this portfolio optimization problem, and I've already shown to you that if we solve this problem with a distributionally robust approach, then there is a much better alignment between in-sample performance and out-of-sample performance. So these histograms of in-sample and out-of-sample performance move closer together, and in particular, they also move closer to the true optimal solution. So that's good news. An interesting question to ask is now, what happens to the solution of this portfolio problem if the Wasserstein radius becomes bigger and bigger? So that means we have less and less information about the future of the stock market. Turns out that it's quite realistic that you don't know anything. And in this case, one can actually show that the optimal portfolio weights, so these are the percentages of your capital that you assign to the different assets, one can show that these portfolio weights will converge to the uniform weights, so basically the portfolio that assigns the same weight to each asset if the ambiguity becomes huge. That's quite a nice result because there was a very well-cited paper by Victor de Miguel and co-authors where he showed that this so-called 1/n portfolio, the portfolio that just naively, without optimizing anything, assigns the same amount of money to each of the assets in a stock market, that this portfolio is extremely hard to beat with any other method. Okay, this, especially actually if you use some kind of a Markowitz approach, or using, in particular if you use the sample average approximation, then you heavily overfit and you heavily suffer from this optimizer's curse, and the out-of-sample performance is really, really poor. So not optimizing at all, in this case, turns out to work better. This here shows that this empirical finding can be explained by a huge amount of ambiguity about the asset return distribution, because the 1/n portfolio is optimal in the limit when epsilon goes to infinity. That's sort of an interesting finding. Okay. Last thing, we can also look at what happens when the sample size becomes bigger. So the number of training samples. Of course, I've told you that theoretically we have asymptotic consistency. So if the number of training samples goes to infinity, we will eventually recover the solution of the true problem. Now, here the red line represents the optimal value of the true problem, which we cannot solve unless we know the true distribution or have infinitely many samples. I solved the portfolio problem with the sample average approximation and with the distribution robust approach for increasing sample sizes from 10 to 1,000. For each sample size, I solved it several times to get basically some confidence intervals for where the results live. So as expected, the solution of the sample average approximation problem is too optimistic. Especially if the sample size is low, it heavily underestimates the risk of the optimal portfolio. Of course, as n goes to infinity, the sample average approximation will work well and will converge to the true solution, but it will do so from below, from the optimistic side. The optimal value of the distribution robust optimization problem is designed to give an upper bound on the true optimal value, right? So it's pessimistic, but it will also converge to the true solution as n goes to infinity. But it does so from the pessimistic side. So this is what the optimizer sees when he or she solves the optimization problem. So that's what the optimizer thinks to get. The SAA optimizer is too optimistic. the DRO optimizer is too pessimistic. That's before the fact. Then when the optimal decision is implemented, that's after the fact. So what these different optimizers actually get is visualized here, right? Again, if you solve the true problem, the out-of-sample performance of your decision will be equal to the optimal value of the true problem. That's again the red line. Of course, no policy, no investment decision can do better than the optimal solution of the true problem. So all the out-of-sample performance values need to be higher than the red line, which is the optimum you could attain. Out-of-sample, you cannot go below, right? So what you can see here is that the SAE approach, out-of-sample performs worse because it's systematically above the distribution robust approach. Now, in the distribution robust approach, there is one thing one needs to carefully consider, and that is the radius of the Wasserstein ball. That's a tuning parameter that you have to choose. I've shown you at the beginning a formula for how you could choose this radius to guarantee that the true distribution is inside the ball. But as somebody remarked, this radius involved some constant c that the authors of the paper didn't disclose to us, so we actually don't know what that radius is. So in practice, you couldn't use that formula. That's actually just nice theoretically, but in practice, you need to do something else. And it turns out that what you should do is something that people do in statistics and machine learning. If you solve a least squares problem or a support vector machine problem, you see that your classifier or regression model will perform much better out of sample if you put a regularization term to the objective function. But then you have a tuning parameter. That's the weight of that term. And this tuning parameter is usually chosen by cross-validation. Okay? So what does that mean? You put aside some of the training samples. Using the other training samples, you solve your distribution robust problem for different choices of the radius. For each choice of the radius, you get an optimal solution. You see how well it does on the training samples that you put aside. The one radius that performs best is the one you choose. With this radius, you then resolve the problem using all the training samples, and that gives you the solution that you then actually put in the out-of-sample result here. So the green curve on the right-hand side, that's the one where the radius was calibrated using cross-validation. There's also a yellow curve which performs super well, right? That is when I would actually cheat and give the distribution robust optimization an infinite number of so-called validation samples that it can use to tune the radius. So I only give it n samples to solve the problem, but I give it an infinite number of samples to tune the parameter, which you can't do in reality, right? But what this shows is that among the types of solutions of the distribution robust problem that you have, there are some that are extremely well. If you just could tune this one parameter, the radius, very well, you could find them. Okay? Maybe it would be interesting to figure out how one could get to those solutions. They are somewhere there. You just need to tune one parameter. Doesn't seem to be too much of a challenge, but in practice maybe. Okay, so that brings me to the end of this exhausting lecture. Thank you very much for the lots of questions and for following closely. If you would like to know more about this, then you can look at particularly the first reference. And if you have any questions, then I'm happy to take them now or later, or you can always drop me an email as well if you're interested in anything of this and would like to know more about it. Okay, thanks a lot. Yeah.